Hello everyone. So I hope you all are doing good. Today I will be explaining this idea that is called contrastive language image retraining, also known as CLIP. This idea was presented in learning transferable visual models from natural language supervision. This was presented in ICML 2021. It has citations around 27,000. This is the author list. As you can see, all of them they belong to OpenAI, which is located in San Francisco, USA. This is the presentation outline. First, I will talk about the introduction of the clip. What are the things that can be done using clip? The motivation behind making clip and what are the research goals? The dataset that has been used for this research, some technical details, applications, results, strength and limitation, and future direction and conclusion. So, as an introduction, CLIP, which is a contrastive language image retraining, is a groundbreaking model that bridges gap between computer vision and natural language processing. We will see later on what does this mean by the combination of computer vision and natural language processing. So, what CLIP can do? CLIP can be used in the healthcare, can help in the classification of medical images, can be used in the e-commerce, can automatically categorize and tag product images based on their text descriptions. It can also be used in the content moderation, where it can help to detect and flag inappropriate content in images based on NLP. On the right hand side, you can see uh, different classes of images on which clip was trained. Either it is the class of cat, dog, uh, a bike, or a car. So you can see that a vast variety of dataset has been created in order to train CLIP. And yes, it is created. No dataset has been used. A new dataset has been created, which we will talk about it in the later slides. So what is the background? The background is that there are challenges in the traditional computer vision. What are the challenges? The challenges lies in the limitation of supervised learning. Supervised learning, let's see an example here. So in a supervised learning, you have a labeled dataset and your model trains based on this labeled dataset. So for example, we have the image of apple and orange. We have different types of apple. We have different types of images of orange. Now, after training, our model can predict an apple or an orange. So if we give it a test data that has images of apple and orange, which are not present in the training set, will our model be able to predict this apple and orange correctly? The answer is yes, because our model has been trained on the similar images. But what if we give another kind of fruit for it to classify? For example, a banana or a pineapple. It will not be able to do that because the training set does not contain that particular fruit. So this is the major issue because the traditional computer vision models they rely heavily on the supervised learning, which means that they need a labeled dataset which has specific fruit in it or specific details for it to classify it correctly. This is not only expensive and time consuming but also limits the model to predefined categories, hampering their ability to generalize across different domains. So if we talk about the current training paradigms, supervised learning using ImageNet. It means that the current supervised learning, it uses ImageNet. This is the most conventional approach in supervised learning. Basically, ImageNet is a dataset that is available and it is a big dataset containing a million of images and it has been trained of thousands of classes and it can be used as a the model trained on this data set can be used as a pre-trained model for different classification or regression task. So the model trains on this ImageNet dataset can contain several problems. Because most of these models they are trained for a specific task, so in order to do or make a model for a different task, there comes the issue of flexibility and scalability, as discussed here as well, that a simple task of classification of apple and orange can cause problems for other fruits classification. So this becomes a motivation for the presentation of clip. So manual labeling of dataset it requires a lot of effort and time, making it highly inefficient. Sometimes it becomes impossible to label the visual concept because of different variations in images. This gives rise to more efficient learning mechanism. The other important motivation is the generalization requirement. Generalization requirement means that a model that has been trained on one specific task can actually perform better on other tasks as well. So this is a generalized model. The generalized model should perform good for all similar tasks for better generalization. This is what a required thing from a good AI model, that it should generalize well. This also comes from the inspiration from NLP. The advancement in AI has trained models on vast variety, making it well suited for generalization. Since this NLP, the natural language processing, it contains a lot of data set and the clip has the same motivation as NLP. This means that the clip uses large amount of data set for training and it can also generalize well. Here you can see the example of manual labeling. The document is sent to either a machine or a computer or a person, and that person has to either confirm that whether this is a spam or not, and if you confirm it, and then this single document is labeled. So you can see how tedious this task is and how much time it will take for all the documents to be labeled. So this actually distinguishes the narrow AI versus the general AI. The general AI is the main motivation behind CLIP, and the narrow AI is basically what our current supervised learning does. Let's dive into the dataset we have. So this dataset consists of 400 million image text pairs collected from the internet. It is designed to ensure the diversity and coverage of different multiple domains. Unlike the traditional dataset, the images are not explicitly labeled. What I mean by explicitly labeled is that, for example, if you see the image of a cat, it is not said that it is a cat, whereas a description has been sent along with this image, that is like a facial photo of a tabby cat. For example, for a horse, it is a black and a white silhouette of a horse, not just an image of a horse. So there is a text description along with an image. We will see how these two work together. So data is sourced from a publicly available images and their associated text that is found online. And examples are image captions, alt text, and web content. All have been gathered together in order to make this dataset. This dataset was not previously available. They made it for this particular problem. So that is also one of the contributions of this paper. So let's dive into the architecture of CLIP. So CLIP aligns the images and text in a shared latent space for a seamless multi-model learning. First, we will give a broader picture and then we will talk about each of the component in detail in order to get a deeper understanding of what CLIP does and how it does. It uses contrastive learning to train two separate encoders, one for images and one for the text. As you can see, these are the bunch of images we have, and these are the bunch of text that we have. The images are passed to the image encoder that forms a image embedding. The text is passed to the text encoder that actually form textual embedding T1, T2 until Tn. So the high level components that we have are image encoder. It converts the images into a dense feature embeddings as we have seen here. So in this paper, they have tried with ResNet and Vision Transformer as an image encoder. For a text encoder, it converts the text into text embedding. The example that they have used in this paper is a similar architecture like Transformer, like GPT. We all have heard about like how GPT performs and how GPT is using and manipulating data nowadays. So this is resulted into a shared latent space. Both our embeddings are projected. For example, this is the image embedding and this is the textual embedding. Both will be multiplied, like I1 will be multiplied by T1, I1 T2, I1 T3 up till I1 Tn. Similarly for I2 T1, I2 T2, I2 T3 until I2 Tn. And for the rest of these embeddings. The now here a good thing is that they have trained this shared embedding space with a contrastive loss function that aligns the similar image text pairs and separates the dissimilar ones. What I mean by similar and dissimilar one is like these are all the pairs that are dissimilar. And in the diagonal, you will find all the pair of image and text that are similar. It means that in the diagonal we have the pair. For example, it can be for here the text will be a cat and a photo of a cat, uh, and for that particular text we will have an image of a cat. So they both will be similar. Similarly, for T2, it can be an image of a dog, a text showing that it is a dog, and for I2, it will be an image of a dog. So they both will be together. So the idea here is using contrastive loss, which we will talk about in the later slide, how contrastive loss work and how contrastive loss is used in order to maximize this embedding and minimize this embedding. Let's talk about each of the component in detail. This was a bigger picture of clip architecture. So first and the most important feature of a clip architecture is the image encoder. So what image encoder does? Image encoder converts the image into vector embeddings that are numerical representation of images encoded into a low dimensional vector representation. We all know that a computer can understand the language of zeros and ones. So in order for a computer to understand it, we need to convert it into numerical embedding. For example, this is an image. For each image, we have different filters, and that filter actually converts that in particular patch of image into different dimensional space. And for each pixel, that pixel will be represented by its numerical value. Like for example, you can see here the white pixels are represented by values that are closer to 255, whereas a black pixel have been represented with the values close to 0. So for this particular paper, they have tested with two image encoders, that is ResNet 50 with the variant of 101. It was introduced in 2015. Another variant is Vision Transformer that came in 2021. The image encoder helps in extracting meaningful features from raw image data. For example, what is the curve? Where is the curve of an image? Where the color changes? What are the objects in an image? So these are some of the high level things that are being extracted by an image encoder using image embeddings. So whereas the embedding it generates helps in reducing high dimensional data of raw images into compact representations. For example, this is a high level data for a computer. It cannot understand it directly. So for that, we need to convert it into numerical representations for in order for machine learning language or a machine learning model or a deep learning model to understand. The second thing is a text encoder. So a text encoder converts natural language text into a vector embeddings, which are numerical representation of the semantic meaning of the text. So what does it mean? It converts, for example, we have this text, canine companion say, we will pass it into the embedding model. And for that, it will generate different uh, vector space. So all of these will have like some kind of value for each of this individual text. So in this paper, they tested with the transformer-based text encoder, which is inspired by the model like ChatGPT. Here it's like using the GPT model. So for these text embeddings, uh, this text embedding uh, are processed by the embedding model here in order to extract some semantic features. So semantic features mean the text that have some kind of context in it. Like similar text will be closer together, whereas a dissimilar text will be far apart from each other. So it encodes the text into a low dimensional representation. For example, here it was a bunch of text, a complete batch of text that after passing through a text encoder, it went through a one dimensional space. Previously, it was in a different dimensional, a higher dimension. But after passing through a text encoder, it was converted into a one dimensional space. The text embedding is allow the model to align the text descriptions with the corresponding images in the shared latent space. As we talked earlier, we made already embeddings for the image like I1, I2, I3, and here we form the embeddings for text as well, T1, T2, T3. Now, what is this shared latent space? The purpose of this shared latent space is where the image embeddings and the text embeddings are projected to align them based on their semantic similarity, based on their context, based on their understanding. We want to create this latent space. This latent space is where our image encoder will give our image embedding and our text encoder will give our textual embeddings. They both will be multiplied together using matrix multiplication and we will get this shared latent space. So here this shared latent space is trained by using contrastive loss. It trains the model by pulling the matching pairs closer in the space and pushing the non-matching pairs farther apart. We will see how it does this in the next slide. This makes the model to have zero shot capabilities. So zero shot means that a model that is able to perform good on the things or the data which it has not seen. In short, it means zero shot just means having the power of generalizability for making a good prediction for all the data that the model has not seen in the training. By aligning the visual and textual data, the models can generalize to new tasks without acquiring additional task-specific training. This contrastive loss is made by using cosine similarity. Cosine similarity measures how far are the embeddings in this shared space, enabling comparison between images and text. We said here in the contrastive loss that we will pull the matching pair closer in the space and we will push the non-matching pairs farther apart. These are all the non-matching and this in the diagonal are the matching pairs. So as we said, we will match these pairs. So this matching will be done by using cosine similarity. So contrastive loss actually uses cosine similarity in order to match or push. Like pulling or pushing is done using the cosine similarity. Let's see what cosine similarity and contrastive loss is in detail. So what is cosine similarity? Cosine similarity is a metric that measures the angle between two vectors in a multidimensional space. It checks how similar two embeddings are based on their domain. So, for example, we have a multidimensional space like three-dimensional space, and in here we have two embeddings. Like it can be represented as Ti or it can be represented as Ii. And now these embeddings have are perpendicular, so their angle between them is 90 degree. So when we try to find out this cosine similarity, for example, A is basically Ti and B is basically Ii. So this basically will give us 0 because this dot product is basically cos, and this cos here is basically the angle is 90. So this cos 90 will give us 0. So this shows that in order to have a maximum similarity between the two vectors, they should be maximized, maximum overlapped. Like for example, like this. This should be Ti and this should be Ii in order to have the maximum cosine similarity. So what they want to do here is they want to maximize the similarity. In order to maximize the similarity, the two vector spaces should be in the similar direction. So this is the formula where A and B represent the two embeddings. You can say A is a textual embedding, B is an image embedding. A dot B is a dot product of two vectors, and this represents the magnitude of length of vector A. This represents the magnitude of length of vector B. So why cosine similarity is being used in the contrastive loss? Cosine similarity actually measures the angle between two vectors as I have shown here rather than their magnitude, means it focuses purely on the direction of the embeddings. This is important because the embeddings may differ in scale, that is length due to variations in the feature intensity, but their alignment direction indicates similarity. What it means is like for example we have textual embedding and image embedding, so the both can have a different magnitude in term when we convert them into the vector space, but their angle will tell us about their similarity. So that's why the cosine similarity is really popular in contrastive loss, because it tells us by finding the angle between them, by between the two vectors. So now as we have discussed cosine similarity, let's discuss contrastive loss. A contrastive loss is a function that ensures the alignment of matching pairs and separation of non-matching pairs. As we have seen earlier in this slide, in the latent space slide, that this shared latent space is actually trained using contrastive loss. So this is the formula for contrastive loss. Contrastive loss computes loss using paired learning. What it means is it makes two pairs, a positive pair and a negative pair. Positive pairs are adjusted to have high cosine similarity, whereas negative pairs are adjusted to have low cosine similarity. So here this numerator factor is basically cosine similarity between the image and its pair text for a positive pair. Whereas, as you can see here, the summation from 1 to n is basically for all the remaining embeddings, it is the cosine similarity. So in the numerator, we have the cosine similarity for only the diagonal pairs, right? As we have discussed here. So this embedding here is shown in the numerator, whereas in the denominator, we have all the remaining embeddings that we want to separate apart. So it means that if we have a bigger amount of denominator, then our loss will be smaller. It means that our value is still close to each other. But if we have a bigger numerator, then our loss will be bigger. So in this way, the contrastive loss actually trains the model by using cosine similarity. Now, after completing this step, the model is actually pre-trained. It means that now it can use this text encoder in order to in order to make testing on the new images that is given to this text encoder in order to decode it. So what happens in this pre-training step? The image text encoder processes raw images and generate image embeddings as we have discussed earlier. The text encoder it processes paired text descriptions and generates text embeddings. Both these are embeddings are aligned and are shared in the latent space. So this is just a recap as what we have learned so far. So what is the role of contrastive loss here? Bringing embeddings of matching pairs like I1 T1, I2 T2, I3 T3 close together and pushing apart all these other embeddings. We don't want them to have similarity. Based on this, the outcome is that the model learns a general mapping between image and text modalities. It means that the model knows, for example, if the image is of a cat, then the model will have a similar image of a cat. Same goes for the dog and other classes. So, in after pre-training, we can have this dataset classifier, which is here in the form of a text encoder. So what it does is it input a set of label, for example, a plane, car, or a dog. It convert these labels into a natural language prompts. For example, for each of this label here, plane, car, dog, bird, we will have like this text along with this object. For example, a photo of a plane, a photo of a car, a photo of a dog here in this textual embedding. And each of these will actually use in order to make a classification result for our text for our image encoder. We will see in the next slide. Let's check it out. So this is the complete model after the training part, and this is basically zero shot prediction because previously we had this image in our training set, right? But now this image is from different domain and now we want to know what this image belongs to. So this part is basically uh, let's see this with the help of a marker. So this part is basically pre-trained by using clip, and now the our text encoder knows how different images looks like, right? So because we made a pair of these and we have done contrastive loss using cosine similarity, so now when if we give our image encoder an image, then after forming the textual embedding close to the image embedding, we can find out that this image is of a dog because we will know that the image belongs to a dog category based on the textual embeddings that we have and the cosine similarity between the dog class. So these are some of the applications of clip. Clip can be used for a noise removal. As an application, clip is used to identify and remove noise from images by aligning noisy images with their clean textual descriptions. It has a practical use case as well for enhancing image quality in medical imaging, photography, or surveillance system. Original image is on the left with the removed noise on the right. The other application is an image search engine. So a clip powers image retrieval by allowing users to search for images with descriptive text, even if the images lack tags or metadata. So it was first found by Vladimir. He posted it in the on Twitter as well, and he has his own GitHub repository. I have given the link in the description. So in here, he used Clip as an image search engine by giving textual prompts, following a few of the examples. So two dogs are playing in the snow, and these are the results that are retrieved by Clip, and these images are from the internet. The other is image generation. So a clip can help to generate images when combined with StyleGAN. So for example, if you see this prompt in a textual form, that is a pencil sketch of people in the rain. So it has generated this. So if integrated with some other models like StyleGAN, it can help us in generation of image. Now let's talk about the results. So this first graph here actually is a comparison with zero shot clip. So they have actually talked about clip as zero shot. So zero shot is basically which is not domain specific and which is generalizable. So they are giving giving a characteristic to clip by saying that it is zero shot. So what they have done here is they have made a comparison with clip versus ResNet 50. So this ResNet 50 is basically a logistic regression. They have trained a ResNet 50 based on the logistic regression features on top of it, and it is fully supervised. If we see here, they have actually made a comparison between 27 dataset. So starting from the Stanford cars up till set, these are the name of 27 dataset. And among these 27 dataset, Clip has performed better on 16 of them. Like until Pascal VOC 2007, it has a positive performance. So it performs the baseline by 20% on these. Like for example, for some of the dataset like Stanford Country 211, Food 101, it performs even better than this baseline, right? So these baseline, they are trained specifically on these data sets, and they are based on the supervised learning. And even after training on supervised learning pattern, they are still not better than uh, Clip. And Clip being a generalized, a zero shot learning framework, it is still giving us good results. So this is a huge, tremendous amount of improvement. And some of the lower performance on a specialized and complex data set such as this satellite image task, limb node, and tumor detection. So these are some of the data set, like for example, data set is about the satellite, and MNIST data set, we know these about the handwritten counting from 1 to 10, so 0 to 9. So these are some of the low performances. You can see like until the performance has shown like minus 37.1 also in one of the data set. And it is because these data set, they are actually domain specific, and it needs a lot of training based on that particular topic. So if we talk about another result, so this is basically they have shown a comparison between the general floating point operations per image over the average score. So this actually tells us the computational cost. So all these in the star are basically different variants of clip. So this basically the star 336 is a pre-trained clip model that has actually 336 pixels, and this has shown the best performance, like around I think 88% of average score, by using the minimum amount of computational cost. So they made a comparison by making by fitting a linear classifier representation extracted from a model on top of the MI clip VIT, and they actually checked that how good Clip performs when compared with other models in terms of the computational cost. So in terms of computational cost, we can see that Clip has performed way better. So on the last result, There we have shown the robustness to natural distribution shift. So for example, we have here different dataset examples. One of the example is from the ImageNet and it is from the banana class. And these are some other examples from ImageNet V2, ImageNet R, ObjectNet, ImageNet Sketch, and ImageNet A. So these are five other classes along with ImageNet. So they have shown the different variety of banana in this data set, like the distribution shift, we call it. And then they have made a comparison with ImageNet ResNet model and zero shot clip. So the ImageNet ResNet model has been specifically trained on this data set, could not perform well, whereas a zero shot clip, which was like trained on generic data, uh, has like better performance. Like even if you talk about the ImageNet R dataset, it has shown like plus 50% improvement, and in the ImageNet A it has shown like 74.4% improvement. So this is huge performance shift. Zero shot clip significantly outperforms the ResNet 101. Zero shot clip is more robust to natural distribution shift. Like for example, if you have some variation in your data set, then the likelihood of zero shot being performing good is much more. So what are the strengths of this clip model? It performs zero shot learning. So clip excels in classifying images without any task specific training. As we have told earlier that the clip model, it has trained on a large data set, so it does not need any specific domain specific data set to perform well. Its ability to generalize across multiple data set is transformative. The other important thing is multimodal alignment. The multimodal alignment aligns images and text in a shared latent space, enabling seamless text to image and image to text task. The other important thing is the flexibility across domains. This is almost same as the zero shot learning. It worked well for various applications like image retrieval, classification, and some other creative tasks. It requires no fine tuning for new tasks, reducing computational cost. As we have seen in the previous example in the results, that no fine tuning was done, even then it was showing a better performance than the task specific models. The other thing is robustness. It performs well even on the out of distribution dataset and corrupted inputs. It handles complex and noisy data better than many traditional models. Now, talking about the strength, what are the limitations? So, the limitations are it has high computational requirements. It requires significant computational resources for training due to the scale of the dataset and model complexity. As we have shown that the dataset that it has been trained on is like 400 million image and text pairs. So you can just imagine how much computational cost it 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 bared in the training part. Then it has the dependence on text prompts. The quality of the result, it depends upon how well the text prompts have been described the task. So crafting effective prompts requires human expertise known as the prompt engineering. The other thing is lack of interpretability. The embeddings and the decision making process are not inherently interpretable, making it challenging to understand why certain outputs are generated. So we cannot say about certain, like for example, because these embeddings are generated uh, in a shared latent space, so there can be sometimes confused generation of text from an image. Like it cannot perform well on some very specific task, like we have seen from an example from the satellite data set. The other possible future direction is like fine tuning for domain specific applications. We can use some parameter efficient fine tuning methods like LoRa, which is a low rank adaptation, to adapt clip for specialized fields without retraining the entire model. The other thing is the integration with generative models for image generation, as we have discussed earlier. There are some already existing applications as well. So instead of combining it with StyleGAN, we can combine it with DALL-E 2 or something like this for making more promising image generation. And then we can also advance zero shot learning, so explore contrastive tuning to improve performance on complex tasks with minimum label data. We can extend the zero shot learning to video understanding as well, because currently we are limited to the images only. It can enable the tasks like video captioning and scene detection. So as a conclusion, this clip is basically a multi-modal alignment. Multi-modal is basically image and textual embedding together, and it bridges the vision. Vision is basically from image encoder and language from the text encoder. We said earlier that we will talk about that how the clip actually bridges uh, co- the computer vision and the natural language processing. So this is how vision and language by aligning images and text in a shared latent space. It also performs zero shot learning, which is that the model performs tasks without task specific training, demonstrating remarkable generalization. The other applications are that it gets used for image classification, retrieval, noise removal, and creative tasks like text-guided image generation. So for the future impact, Lip's approach lays the foundation for next generation multimodal AI applications, driving innovation in diverse fields. So these are some of the reference papers. This one is the original reference paper, and this is some follow-up work, and these are the YouTube tutorials for better understanding. So if you have any question, then you can ask me using this email address. Thank you. Hello everyone. So here we will implement the model clip. So there are several methods that you can use in order for the implementation. You can make your own environment like I did here, a virtual environment, and then you can run the GitHub code here for clip, or you can use the Google Colab link for clip. I think the Google Colab one is much more easier. In that case, you don't need to make the virtual environment or creating a separate environment for the implementation. So here we have first we will run this code, and then this will clone the clip model. Then we will install some necessary libraries, like for example the PyTorch, and this is the PyTorch along with the CUDA version. And if we load the clip model, so there are several model available as we have discussed in the paper as well. ResNet 50, ResNet 101, and these are the different variants of Vision Transformer as well. So Vision Transformer base, and then if we load this Vision Transformer base model and run it, and then this will actually give us different model parameters. So if we check it, the model is quite large and deep, and it is like around 151 million parameters it has, and the input resolution of the images is like 222 which is like basic for most convolution and transformer models. And then the next two parameters are for the textual embedding, that is context length and vocabulary size. And then if we define the pre-processing stage, image pre-processing contains some steps like resizing of image, interpolation, and then center cropping it, then also converting it into tensor, and then like normal image normalization. So this image normalization has been done using the ImageNet dataset, where we have calculated the mean value and standard deviation for each of the three channels that we have in the RGB image. So then if we run this code, it will actually tokenize this hello world, actually create separate embedding for each of the alphabet that we have here, and assign different token ID to each of them. And you can also check the shape of this. And here, if you see, this is 77, as we have discussed earlier, that the context length for each embedding is 77. Uh, so you can also import make a dictionary for it. Like these are basically the description dictionary. It defines a dictionary mapping file name, example page and coffee to natural language descriptions of their content. Like for example, a page of a text about segmentation, which we will see these examples later on. And then this is basically an image processing step. Uh, Pre-processing step, and here you will load images from the Sky image data, and for each image it opens the image and converts it into the RGB format using PIL and applies the pre-processing transformations. It displays the images with its corresponding description. It appends the images and descriptions to list for later pre-processing. So this is how the dataset looks like, as we have seen in the uh, paper presentation as well. Like for example, this is a horse, and the horse is basically a black and a white silhouette of a horse. This is the description along with the image. So this is how the embeddings are created by combining these both spaces together in a shared latent space. And if we see here, it's basically about image and text features extraction, and it converts the preprocessed image and tokenized text into the GPU tensors, and it uses the clip model to extract image features and text features like here. And then is the step for the normalization and similarity calculation. So here we have first normalize it, and then we will calculate the similarity using the dot product. And uh, then next we have here what we have calculated is basically we have calculated the cosine similarity between text and image features. So here are all our image embedding, and here we have our text embedding. And as we have seen in the presentation slide also, that we want to maximize this diagonal, and the rest of the thing we just want to minimize it in order to make the maximum similarity between the text that has common, like the text that is same with the image, in order to make a maximum similarity between these two. So this is basically a visualization summary that displays the cosine similarity matrix as a heat map, and it annotates each image and text pair with their similarity score. Uh, then we have what we have done is we have used Cipher 100 dataset, and uh, first it downloads it and then applies the same pre-processing pipeline that we have done for previous images, and it generates the embeddings for text labels and compares them with the image features to calculate the class probabilities. So let me show you here. So this is the class probabilities. These are the results. Like for example, some of the results are really good. Like for example, for the rocket, it has shown the class probability of almost 1. And this is an image of a man, so it has shown class probability of man. So as I discussed in the paper, that the text encoder, it actually makes the embedding for each of the object that it has in the data. Like for example, a picture of a boy, a picture of a man, a telephone, plane, woman, and then there will be some probability, and this probability distribution is the result of this probability distribution is basically from the cosine similarity. So this horizontal bar chart actually shows the top 5 predicted classes and their probabilities. Like these are the top 5 classes, and the probability of the maximum class is, like as you can see here, it has predicted very nicely here as well. But for some of the images, it cannot like generalize well, and especially for the task specific images. So that's all for the implementation of the code. Thank you for listening to my presentation, and if you have any question, you can ask in the ask uh, using my email address. Thank you and enjoy your vacation.